All right, let's go on page 46 when we're done. Today we're looking at change in linear and exponential functions. So really this lesson ties together the sequences we've been talking about with the functions, but I kind of did that as we learned it, especially with the arithmetic. So this at the beginning, it's kind of more of the same, kind of trying to draw it together, but I've really already done that. Some things are written just maybe a little bit differently. So in the last section, we learned that arithmetic sequences behave like what kind of functions? Linear, okay? And that geometric sequences behave like exponential. Okay, so we're halfway there. So we're looking a little bit more closely. Again, we kind of already did. So here are our little formulas for arithmetic sequences and linear functions. And we really, truly don't really even care about these two because we did them that way and then just put the ends in there. We don't really care about the k's and the other stuff like that. One thing that we have to make sure that we understand is we've understood for a long time that we've got x, y for our linear functions, and that for our sequences, our input is n and our output is a sub n. And n has to be a whole number for a sequence because it's like the term number. And then this form here of that little formula that we didn't really care about mimics the slope-intercept form. But notice we wrote y equals mx plus b, and this has b plus mx, right? But it's the same thing, yes? It's not about exactly, what order the letters are in. It's like where they are, what they're related to, and they all kind of mean the same thing, okay? But they have it written this way because it more closely matches this, which is more of the statistical way to look at linear data. And then point slope form, what we actually wrote is the actual point slope form that would be on a formula chart is y minus y1 equals m times x minus x1. Then we just solved for y by moving over that y sub 1. So y equals m times x minus x1 plus y1. Okay, so that's what we were doing yesterday. Again, that's what this is. They just have these two terms flipped around, which is 100% fine. But that throws y'all off sometimes, especially when we do transformations, and you're used to like the +5 at the end is like your vertical shift or whatever. But if they put it at the front, it's like a whole new thing, and then we make up stuff and don't know what's happening. That happens a lot with transformations if this is if that's a negative. If it's a positive, usually it's on the end, but it doesn't matter, right? It's just, it means the same thing. Same thing is happening here. Okay, we all good with all that? I think that's all I wanted to say about those, yeah. All right, so then we have geometric sequences, and we did kind of, again, we didn't really care about the n's and the k's. I did show you this yesterday, which you could also, for functions, have it written like this. You rarely would see it with an R, but you could. It just, again, it means the same thing. This is more likely how you have seen all of your exponential stuff. Maybe like this, which is basically what we ended up doing. I just didn't even write that down. I didn't want that to freak you out because it's another little formula. We don't necessarily need a little formula to plug stuff in. We just need to know where to put stuff to set it up. And it's fairly simple. If we practice a little bit, it's going to be fine, right? But again, for exponential functions, we have x, y. And for geometric sequences, it's n g sub n. Okay, we all good? Just kind of summing up the last couple of days. All right. So it's important to recognize and understand the similarities and differences between linear and exponential functions. Well, visually, I think that there are, it's pretty obvious the differences, but also when you're talking about them functionally and some other things. But so for our linear functions, it says, and notice this terminology here, over equal length input value intervals. Okay, we've written that a lot. And if you're not used to writing that, or you've never heard that before, you haven't been paying attention and you haven't been writing down stuff you should have been writing down, right? Because that's a big part of these answers. Over equal length input value intervals, the output values change at a what for linear? How do the output values change? Constant. Good. Change at a constant rate. Okay. So the change m, your slope, if we just think of, if we think about an arithmetic sequence, you're adding the same thing to each term, right, to get to the next one. So the change is based on addition. Even though you're multiplying the slope times x, that's not what we're talking about. You're adding the same thing every time. That's why it's changing at a constant rate, okay? For exponential functions, over equal length input value intervals, the output values, they don't change at a constant rate. How do they change? By a ratio, yes. So proportionally is what we would say, but yes, absolutely, proportionally. Okay. So the change B, so for exponential or for our geometric sequences, instead of adding the same thing every time, we are multiplying by the same thing. So this is based on multiplication. And notice this says addition and multiplication. There's no use of the word subtraction or division. So if you have like a negative slope, so and you think about it, I'm subtracting the same thing every time. No, you're adding the negative number every time. You're adding a -2 or adding a -3. Same thing with multiplication. We're not going to say, oh, we're dividing by 2 every time. No, we're not. We're multiplying by 1/2. Okay, so you have to talk about them as multiplication and addition. All right. So with both of these, what we've done over the last couple of days is if you have 2 points, you can write an equation of a linear function, exponential function, arithmetic sequence, or geometric sequence. Now, they'd have to tell you what you want. Otherwise, you have no idea, or have some context to it, at least, if they didn't flat out tell you. But 2 points, if I know it's supposed to be exponential, I can do what I need to do to fill that out. What 2 points is not enough for is to identify. If I just give you 2 points and say, is this from linear or exponential, you'd have absolutely no idea without more information, unless there was context given to it. Okay, we all good with all that? Awesome, flip it over. So here, selected values of several functions are given. For each table, determine if the function could be linear, exponential, or neither. Now, we've already done linear and quadratic, like linear, quadratic, or neither. We've done what is the degree, where it could have been a 3rd degree, 4th degree. So maybe some of these are quadratic. If they are, I don't care. Nobody's asking me that. We're just looking at linear or exponential or neither, and that's it. So we start all of them no matter what. Now, when I say all of them, I don't mean every single table, because sometimes there's tables and they're not asking you this kind of question, and y'all are still doing this kind of thing over here. Okay, that just means you're just randomly doing that on every table. If I asked you to use this to find the rate of change, you don't need to do all that, right? It's when we're using it to identify. But we're looking for, do we have equal length input value intervals? So 3 minus 0 is 3. This gives me 3, 3, 3. We got to check it every time. You can't take it for granted that it's just going to work for you. So then we're going to check to see if this is linear. So we will do some subtraction here. 5 minus 7, -2. 3 minus 5, -2. 1 minus 3, -2. -1 minus 1, -2. And again, if you cannot add and subtract positive and negative integers correctly, you probably aren't going to be able to get these right. I mean, but you've got to be able to add and subtract. I don't know what to tell you. So since they have a common difference, is this linear, exponential, or neither? Linear, okay? So we are going to say this is linear. Okay, then my reason is, and I have to start them all this way, over equal length input value intervals. Okay, over equal length input value intervals, comma, output values change at a constant rate. So I paused there for a second because in my brain I was like, am I using the right words for this specific question? Because we have done linear before, right? And the way you would have answered that one would have been like over equal length input value intervals, the average rates of change of f are constant, okay? So that's a little bit different than this. If you were asked about linear, how do you know which one to put? You can put either one as long as you use the right words the right way. But my rate of change is constant, or this changes at a constant rate. Do you see how those words are different, but they mean the same thing? And sometimes y'all mix all that stuff together. Now, I'm going to have you actually write this stuff out for me at times so I can know that you know what you're doing and you can put all this together. But in the end, on the actual exam, these kinds of questions will be multiple choice. And your multiple choice answers could be worded like this, or it could be worded like the other one, or they could, you know, the wording can change a little bit depending on exactly, but it all still basically means the same thing. And I know y'all can get lost in the words. That's why you got to make sure you know how to put them all together and what they mean. Okay, are we good so far? Questions? All right, so let's look at B. So we're going to do this first. So that's 1, 1, 1, 1. Great. Equal length input value intervals. Then I'm going to do 1 minus 0 is 1. 4 minus 1 is 3. All right, so I'm doing my differences. Already those two are not the same. So is this linear? No. So don't care about that. So now I'm going to check to see if it is exponential. So now I'm going to look for the ratios. I'm going to put 1 over 0. What is 1 over 0? Undefined. Okay. I had to yell at third period because the majority of them wanted to say 0, and I'm quite sure some of y'all wanted to say 0 deep down in your heart, or that you don't know, or -1, which is usually my favorite. I have no idea where that comes from. But I'm going to show y'all these signs over here again. You see that no? N over 0 is no because it's undefined. Okay, 0 over k is 0. So put that in your brain if you get that stuff mixed up. Don't make me yell no at you. And then I won't say anything else, and you got to figure out why I'm yelling no at you. All right, so that's undefined. And let's say you do that and you're like, well, I don't even know what I'm supposed to do with that for a ratio. So let's just keep going. 4 over 1 is 4. 9 over 4 is 9/4. So now, like, I'm pretty confident that, like, I don't know, maybe we just don't count the undefined. Who knows, right? But those are not the same. So my ratios are not the same, and my differences are not the same. So this answer is neither. I'm going to say neither, and then I'm going to start it the exact same way. Over equal length input value intervals comma output values okay. So up to that point, with the exception of the word neither, the words would be the same on every single answer, okay? But my output values do not change at a constant rate or proportionally. Everybody okay with that? Okie dokie. So let's check out this one. Sort of used up some of my space here, but 10 minus 5 is 5, 5, 5, 5. Okay. Then over here, if I start doing my differences, 40 minus 80 is -40. 20 minus 40 is -20. Is this going to be linear? No. So I'll just mark that out for myself. Then I start doing the ratios. 40 over 80 is 1/2. 40 over 20, or I'm sorry, 20 over 40 is 1/2. 10 over 20, 1/2. 5 over 10, 1/2. So what is this? Exponential. So exponential. And then I bet you could write the rest out. You can at least get it started on your own. I'm sorry, what? We didn't have to name the function on this one. And again, this is, most of the time they'll be written for you, so it's okay that we didn't, because yeah, I don't know why we approach some of these differently like that, but we do. Good question though. Just don't have a great answer, but no. All right, questions? Anything? That makes sense? We good? We can do that? Yes? All right, great. So let's look at example 2. Okay, so this example talks about Mr. Passwater, and I'm not sure if I've told y'all anything about Mr. Passwater before, but he's kind of a guru in the calculus and pre-cal community. He does a lot of work with College Board. He actually is still a teacher in the classroom. A lot of people they'll teach and then they'll go be like consultants for things, and they've been out of the classroom for a long time and they're out of touch and they write stuff and think this, and you're like, you clearly are never in front of actual students. But he is still in the classroom, still teaching calculus, both levels, and teaching AP pre-cal. And he also is very giving of his materials. Like he'll share it. You don't have to buy his stuff or whatever. So there are a lot of his questions that I use. And because he is so generous with all this and does such a great job for everything, I also trust his opinion on things when we don't get clear answers from College Board. That anytime he uses himself in an example, I always like leave that in there, just kind of as a nod to him, but because he's also kind of a pretty funny guy. All right, so a wild rumor is spreading that Mr. Passwater won 3rd place in the World's Strongest Man contest. Mr. Passwater definitely, probably, didn't start the rumor. The number of people that have heard the rumor can be modeled using a geometric sequence. So it flat out told me that right there, right? Where 43 people had heard the rumor on day 3, and 140 people have heard the rumor on day 6. According to the model, how many people to the nearest whole number have heard the rumor by day 10? Okay, so I didn't have to decide from the context, because I don't know that we have enough information from that anyway. They're saying we're going to use a geometric sequence, right? So they didn't give me the rate, they didn't give me the R, so I've got to figure it out, which means I need 2 ordered pairs. My first ordered pair that I could come up with from the information there, what would the input be? 3. Okay, your input would be 3, your output would be 43. Because we got 43 people heard the rumor on day 3. Then my next ordered pair, that's 140 people on day 6. So it's 6, 140. Okay. Geometric sequence. So we're going to start by writing out our G sub n, give us a starting place. And I have to pick one of these 2 points. Which would be the best choice? The left one, right? You take the one with the smallest input value. And so, I first write the output. So 43 times R, which I don't know, to the n minus the input, 3 power. Okay, that's one little pattern you have to remember. Okay, it's not like you have all these formulas for arithmetic and geometric. Arithmetic goes straight with lines. We remember this little pattern and how to substitute it in, and then we're not going to do anything crazy here. Okay, but I need to figure out R. So now I'm going to take this other one, and this is going to be my n G sub n, that I'm going to put into my little blue equation here and get 140 equals 43 times R, which I don't know. Oops, put my parentheses in the wrong place. R, which I don't know, to the 6 minus 3 power. Okay. So we've got to isolate R. I'm going to divide both sides by 43, so I'm going to get 140 over 43. You think those are going to divide evenly? No. And I'm pretty sure 43 is a prime number, but I don't know for sure. I really don't even care at this point. It's fine. This is equal to R cubed. Okay. To undo R cubed, what do? Cube root. So R is going to be equal to the cube root of 140 over 43, which I'm going to tell you is not a perfect cube, and it's going to be a horrific decimal. So we're not getting your computers out to do this in Desmos right now, because I want you to actually listen to what I'm saying. You can find the cube root in Desmos. It's in there. You can go through menus, or you can do little shortcuts or whatever. But sometimes it's just faster and easier to do it a different way. Remember that a cube root is the same thing as like 140 over 43 to the 1/3 power. And in my opinion, it would just be faster for me to just go ahead and type this in than to try and find the cube root or punch stuff in. Okay, but they both work. Okay, we good? Brandon, sit up. All right, so that's R. Now, I could find the decimal for you, and I can tell you what it is right now, but honestly, I don't even know. I don't even have it written down because you never, ever, 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 ever get a decimal in the middle of your computation and plug that decimal back in. That's bad, bad, real bad, okay? So decimals aren't evil. Decimals used at the wrong time are definitely evil. So that's why we just have to be very careful with them. So instead, what I'm going to do is I'm going to come back and I'm going to grab this and I'm going to rewrite it with R just like we did yesterday, but this is R. So this is going to be G sub n equals 43 times, and then my R is 140 over 43 to the 1/3 power, and then all of that is to the n minus 3 power. That is a perfectly acceptable G sub n formula. That is acceptable. You having a decimal in there, not acceptable for a formula, right? Because we'd be rounding it different ways. Our answers will be different in the end, and that's not okay. All right, so there's my G sub n. But I'm going to have to use a calculator anyway, so it's fine. I'm basically just going to do it all together at the end. There's my G sub n. I need G sub 10. So G sub 10 is equal to 43 times 140 over 43 to the 1/3 power to the 10 minus 3 power. Now, we have exponent rules. I know what my power to a power rule is. I don't care. I'm not even going to do 10 minus 3. All day yesterday, I asked what 11 minus 3 was, and I think I never got 8 the first time. Okay, I got 9 and 7 and other, that's where we make our mistakes, right? So when you would be able to do this on the calculator, I'm just going to tell you what the answer is, but you would type this in exactly like you see it, even the 10 minus 3, so you don't mess anything up, and bam, it spits out an answer for you. That makes sense? You just keep it exact until the end. Keep it exact until the end, and use the calculator at the end. Don't start typing things for this, because you still have to have stuff written down. Like, you still would absolutely need to write this down on your paper as your answer before you even type it in anyway, so just leave it like that. So what you would get here is you're going to get that G sub 10 is equal to 675.5758. Okay, that's what the calculator gives you. I know that's only 4 decimal places, and I told you 5, but I forgot to type it in again, and I don't know what the 5th one is, but it doesn't really matter in the end anyway. So that's what I get. Does that make sense for the context of this problem? No, not only does it not make sense, it even says to the nearest whole number. So this is the amount of people that have heard a rumor. Do you think we should round up or round down? Yeah, I mean, you could argue either way, right? It does say but here's the thing. I think you're right. In context, you would probably round down, but then it says to the nearest whole number. And if you use your rounding rules, then you round up, right? And so, like, what do? I don't know. As long as you could justify it either way. That's why this needs to be written down, even though that's not what they asked you for. You with me on that? Because we're not really testing, can you figure what the number of people out from that weird number? It's like, can you do all that to get this weird number so you can answer the question about the people? So we have this. We still need to answer the question. So you can write 675 or 676, whatever is in your heart you think is right. And you would be right either way because we have this and because that's a weird way to ask things, okay? What's my units here? People, okay? We good on that? So even if you're going to round in the end, it is best practice to write down whatever the calculator said, because then that shows the grader that you do understand the math behind it, you can use the technology, you can do all that, and then we also just need to answer the question, okay? What questions do you have? We good? Okay, perfect. All right, so now a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence, okay? Told me exactly what to do. 5th row has 31 seats, 11th row has 49 seats. How many seats are in the 25th row? All right, so my first order pair would be what? 531, very good. Then my next one would be 1149. This is an arithmetic sequence. So what do I use those 2 points to do? Slope. So slope is equal to 49 minus 31 over 11 minus 5. So that is 18 over 6, I believe, which gives me 3. Okay. Everybody good so far? All right, so when we were choosing a point with the geometric, we chose the point with the smaller input value. Here it doesn't really matter. And they're both positive, but if I'm gonna have to actually do some computation with it, because I think it would make sense to pick the smaller number, right? But it really doesn't matter which one I do. But I'm gonna pick this one and get rid of that. So I'm gonna do y minus 31 equals 3 times x minus 5. Then I'm gonna move my 31 over. I equals 3 times x minus 5 plus 31. And then even though it didn't ask me to write an a sub n, I'm going to do that anyway because we need to practice, putting it back in the right form. So that y becomes a sub n equals 3 times n minus 5 plus 31. So there's my a sub n formula. Now I need the 25th. So I need a25 be 3 times 25 minus 5 plus 31. It gives me 3 times 20 plus 31. So a25 equals 91. And that's 91 what? Seats. Okay. What questions do you have? Anything? We good? We good? All right.